Okay, so if there are no other questions, we can start the lecture. Today, the lecture, we're going to do one of our detours. So as I said at the beginning of our class, not everything we do is going to go in a straight line. And one of the objectives of the course is also to try and introduce people to various techniques and calculations that are useful, even generally, apart from various arguments that people have made about the information paradox. So today's lecture is largely going to be a detour into some simple techniques and simple results from quantum information. But before I start that detour, I just wanted to explain what the motivation for this detour is going to be. So as we discussed in some detail yesterday, when one looks at Hawking's original paradox, there is a concrete computational aspect to it, and there is an intuitive aspect to it. And neither of them are really robust enough to give one a paradox, because the concrete computational aspect, you find that just computing some low point correlators is not enough to argue that the final state is mixed. And using intuition from the causal structure is not enough to really argue for a principle of ignorance, given the subtleties in localizing operators and in localizing information in any theory of quantum gravity. So we want to move on now to more robust paradoxes. And these paradoxes, which were first articulated by Mathur and then elaborated slightly by AMPS. And the main point of these paradoxes was to use the monogamy of entanglement, was to use a property called the monogamy of entanglement to argue that these small corrections would be insufficient to resolve the information paradox. And therefore, you would have to do something very significant or accept that there was a mixed state. So let me just try and explain in a few minutes what the idea was, just to motivate why we are going to look at the quantum information results that we are going to look at today. The argument of Mathur and AMPS was that if one has a smooth horizon, if you have a black hole and the horizon of the black hole remains smooth at all times, then in the modes inside and outside the horizon must be entangled if the horizon is smooth. Okay. So we already encountered, in some sense, this result when we did in the first few lectures when we looked at correlators across a null surface in quantum field theory. So we already encountered this result in some form, but there's something that we need to make more precise, and this was one of the starting points of this Mathur and AMPS monogamy paradox. And the second point was that typicality. So if you take a typical black hole microstate, it requires entanglement between modes that are close to the horizon, near horizon modes, and far away modes at late times. And this is true at late times. Okay? And these two demands are in contradiction because so 1 and 2 are inconsistent because entanglement is monogamous. Okay, so this is the very brief summary of the Mathur AMPS paradoxes. But at this point, we are not in a position to make this paradox precise because while we have spoken about correlators inside and outside the horizon, we haven't yet formulated that in terms of entanglement. So there's this phrase entangled, which we haven't made precise. We haven't explained why typicality requires modes far away to be entangled with modes which are near the horizon at late times. And we also haven't explained why entanglement is monogamous. So at this point, these are three statements which might sound plausible. But as I said, one of the things we would like to do in this course is try and make everything we say as precise as possible. And at the moment, we don't have the tools to make this precise. What we now want to do is make all these three things precise, and therefore what we'd like to do is develop a notion of what it means for operators or information or degrees of freedom to be entangled, and then we'd like to explain why it is that people said that entanglement there should be entanglement between modes near the horizon and modes far away at late times, and also why is it that this is inconsistent? What does it mean for entanglement to be monogamous? I want to emphasize that the point of these arguments was that if you look at this, this argument also involves the inside very importantly. So these arguments are going to be different from the arguments that we looked at in Hawking's original paradox because of the underlined word inside, and this makes essential reference to the interior. And it makes not just qualitative reference to the interior in the sense that there are some degrees of freedom in the interior that we don't know about outside, but it's going to make quantitative reference to the interior, and that's the sense in which these paradoxes were different from the paradoxes that Hawking originally described. Okay? So that's what we want to do. We want to basically develop some tools to try and understand this. So we're actually going to develop the tools just abstractly in the rest of the lecture. I'm not going to say so much about I'm not going to say so much about black holes. I'm just going to try and say a few things about entanglement, and then we'll come back to black holes. So the thing is that I want to the original paradoxes were formulated using the entanglement entropy. So original paradoxes used the entanglement entropy, okay? But the entanglement entropy, for those of you who've studied it in any quantum field theory and certainly in gravity, is not necessarily a very well-defined notion. It's not in a quantum field theory. It suffers from UV divergences, and we know how to regulate those UV divergences. But in gravity, no one has really carefully studied what it means to define entanglement entropy in a situation where gravity is dynamical. I mean, there are various proposals, but there isn't really a precise definition. And so one of the questions that people would often ask about this original formulation of the paradox is, you're writing, you're using this quantity which you're calling the entanglement entropy in some region where gravity is dynamical. And how do you know that what you're doing makes sense? And so we want to take a slightly different approach to entanglement, which will take us to the same final conclusion. But we just want to take a slightly different approach. And the different approach is that we want to explore entanglement using Bell correlators. Okay, so what we're going to use actually are Bell correlators. And in fact, we will use a slight refinement of Bell correlators called CHSH correlators, which are, morally similar. But the point about using correlation functions to phrase these paradoxes, to phrase the issue of monogamy, to phrase the issue of entanglement, is that correlation functions are well defined even in the theory of gravity. In the end, even in a theory of dynamical gravity, you expect that there is a sense in which you can discuss quasi-local operators, or you can discuss some field operator. Maybe you need to dress the field operator as we discussed last time, but you can discuss some notion of a field. And then you can talk about correlators between degrees of freedom. And those correlators, you don't expect will receive violent corrections because of something that happens at the Planck scale. And that's the reason, we now want to explore these notions of entanglement, but not using the entanglement entropy, although that's an alternative approach and was indeed the original approach that was used to formulate these paradoxes, but in terms of correlation functions. Okay? So the first thing I want to describe is this notion of CHSH correlators. Okay, so let me start by just explaining that. So let's say we have. So I want to now understand CHSH correlators. Okay, so let's say we have two systems, and one system is A. So we have two distinct systems. I'll explain in a minute what it means to have two distinct systems in quantum mechanics, but we have a system A and we have a system B. Let's just first look at what happens classically. And let us say in system A, we are allowed to make some observations, and corresponding to those observations, there are some random variables or some observables. And there are two observables that we have in system A, and we'll call them A1 and A2. And there are two observables we have in system B, and we will call them B1 and B2. Okay? And the important aspect, a very important aspect of these observables, otherwise nothing we say is going to make sense, is that each observable, okay, so all these four observables that we have on the board, each observable takes values in -1 to 1. It could actually take continuous values between -1 to 1. So as long as, the important part we need here is that it doesn't take a value whose absolute, it doesn't take something which is larger than 1. It doesn't take the value 2, but it could take the value 0.5. In fact, in these lectures, we'll always just consider variables where the eigenvalues are just -1 and 1. But, in principle, everything we say will hold if the eigenvalues have some intermediate, if these observables could take some intermediate values, provided these values are between -1 and 1. Okay. So first, let's just consider the classical case. Okay, so let me try and explain what this is using the classical situation. So it could be, let's say A1 and A2. So A and B are two coins. Okay. And they're two coins, and these coins are kept in like separate boxes. And then you can open the box and you can ask various questions about the coins. And depending on what the answer is, you can assign values to A1 and A2. Okay. So when you open the box, if you find that the coin is, so here's one possible assignment. Okay. So I just want to explain. So let's say if coin is heads, okay, and it's -1 if it's tails. Okay. So this is a possible observation you can make on the box. And A2 is another observation you make on the same coin. Okay. And it's 1 if it's a 10 rupee coin. Okay. And it's -1 if it's a 5 rupee coin. Okay. So it's a pretty straightforward thing. You have two coins. One coin you call A, the other coin you call B. The coins are kept in some box. You open the box. Someone has put the coin in with some distribution. You open the box and you can ask various questions. You can ask, is the coin heads or tails? Is the coin 10 rupees or 5 rupees? And similarly for B. Okay. And you don't have one coin. You can keep playing this game many times. So maybe some of us play this game and one of us puts the coin inside and the other person goes and looks at the coin. And so we can keep playing this game, and therefore you can ask about the expectation values of these operators A1 and A2. If the person who's putting the coin in is more likely to put the coin up as heads, then the expectation value of A1 would be positive, and if the coins are equally distributed, it would be 0. We are not putting any constraints on what kind of probability distribution you could put in for the coins. Okay. But given these variables A1, A2, B1, and B2, the point is to define a joint observable, and the joint observable is the following. And this is what's called a CHSH observable. Okay. So this is a CHSH observable. And it's a pretty simple observable, right? You have some values for B1 and B2, and you take B1 plus B2, multiply with A1, and you have B1 minus B2 and multiply with A2. Okay. So first, let us consider the classical case. Okay. The classical case actually is what we have on the blackboard, where we are discussing two coins rather than two quantum spins. And in the classical case, we can check, we are allowed to assign all these arbitrary values. And every time, we play this game, there's some value assigned to all of this. But it's pretty easy to check that in the classical case, you will always have the mod of CAB is less than 2. Okay. And let me just remind you what the definition of CAB was. Let me just copy the definition of CAB. So you can see why that's the case. Okay. So remember, this is CAB. We'll keep using these kinds of operators. It's a pretty simple definition, so it's easy to memorize. But it's easy to see from this definition that the mod of CAB is always smaller than 2. And the reason is that, notice that, remember that A1 and A2, neither of them can have an absolute value which is larger than 1. And therefore, the mod of CAB must be smaller than the mod of B1 plus B2, if all of these are numbers, plus the mod of B1 minus B2, right? But if you think about it a little bit, this has to be smaller than twice the maximum of B1 and B2. Okay. So the mod of the, okay. And this is clearly smaller than equal to 2. So you can check by just assigning values. Let's say A1 was 1, B1 was 1, B2 was 1, then B1 minus B2 is 0. And so whatever the value of A2 is doesn't matter, and A1 into B1 plus B2 is 2. So you can check for any assignment of values. I mean, it's a trivial inequality that that the mod of CAB is always smaller than equal to 2. And therefore, because this is true for any assignment of the values, it's always the case that if you look at the mod of the expectation value of CAB, this is also smaller than equal to 2. Whatever probability distribution you put for the variables A1, B1, A2, and B2. Okay? So this is a very simple result, which is what's true classically. I hope this is clear, and I hope the setup is clear. What I said was very simple, but if there's something unclear about the setup, I'm happy to explain that.
Actually, there's one question in the chat.
Yeah.
That's why is the specific choice for the eigenvalues taken? Like, why do you assume?
It's a normalization. It's not a, it's just a question of how we normalize the observables. So, if you were to normalize the observables and allow them to take values between 10 and minus 10, clearly this 2 would turn into 20. Right? The inequality I'm putting here is that you have some observables which are 1 and minus 1, and that's why I got a 2. So for this inequality, it was important that I normalize the variables correctly. By the way, in the classical case, there's no notion of eigenvalues, but there's some values, and it was important that you set the values between minus 1 and 1. Otherwise, you could clearly get any value by just taking A1 equal to 1000. And so, this inequality makes sense when you are assigning values between minus 1 and 1. As I said, you could assign values 0.5 and 0.3, but the absolute value of each value you assign has to be between minus 1 to 1. Okay, good. Now, in the quantum mechanical case, it turns out there's what's called Cytosins Bound. Okay, and Cytosins Bound actually tells you that the mod of the expectation value of CAB is not less than 2, but is less than 2 root 2. Okay? So this is the statement that what do you mean by the statement? What we mean is that here in a quantum mechanical state, you could once again have some observables A1 and A2. In this case, you demand that the operator norm of A1 and the operator norm of A2 is smaller than 1. So let me just write that clearly. Okay, so in QM, we have once again CAB is A1 into B1 plus B2 plus A2 into B1 minus B2, right? And the demand we put is that the operator norm. So I'll use this notation for operator norm. So the operator norm of all the AIs and all the BIs is smaller than equal to 1. Okay? So the operator norm of these things, I mean, it could be less than 1, but it should be smaller than equal to 1. And the demand that A and B are in different systems in quantum mechanics is simply the statement that the commutator of AI and BJ is equal to 0. Okay? So AI is probing some degrees of freedom, and BJ is probing some other degrees of freedom. So both A1 and A2 commute with both B1 and B2, and that's the statement that these operators are probing different systems. Okay. Now in quantum mechanics, how can it be that CAB is smaller than 2 square root 2? Let me give you I don't want to prove the bound in general, but I'll give you very easily, I'll show you how it's very easy to find a configuration where this happens. And the basic flaw in the reasoning that in our classical reasoning, which was in the previous board, was that in the classical reasoning, we assigned a definite value to B1 and B2 and A1 and A2 at the same time. But quantum mechanically, it may not be the case that one can assign a definite value both to B1 and B2 at the same time. So when I gave the example of coins, and I said, you could ask if the coin was heads, and you could ask if the coin was a 5 rupee or a 10 rupee coin. There was some sense in which you could assign those values simultaneously. But if instead you had a spin, and if A1 was telling you whether the spin was pointing in the +1 and the -1 direction, and B1 was measuring the x component of the spin, then it would not be the case. Sorry, if A1 was measuring the z component and A2 was measuring the x component, then it would not be the case that you could assign simultaneous values both to A1 and A2, and similarly for B1 and B2. And that's what allows you to violate this inequality. And if you violate this inequality, it's clear that you have correlators that are beyond classical correlators. Okay, so if CAB, and I'll explain how, if the expectation value of CAB is between 2 and 2 root 2, then the correlators that we have are exceeding the maximum allowed value for classical correlators, then the systems are said to be entangled. This is the definition of what it means for the systems to be entangled. It means that correlators between the systems exceed the max allowed classical value. Okay. So this is what it means for something to be entangled. This is sometimes called a Bell inequality, but it's more precisely this. The upper bound is Cytosins bound, and lower bound is the classical bound. Is there a question right here? Yeah.
Yeah. So you said this is possible because B1 and B2 could not be simultaneously diagonalizable.
Correct.
But somehow we end up concluding entanglement across the regions. Right?
Entanglement between system A and system B.
Right, but this expectation goes up from the classical expectation because of something more some local feature of section region B or region A.
Some local feature of both region A and region B, in that the observables A1 and A2 do not commute, and the observables B1 and B2 do not commute.
And but the conclusion seems to be like something across the regions, saying that they are entangled.
Indeed, yes, the systems are entangled, but the question is
the question is the reason you can go beyond the classical boundaries because of some local property of region A and B separately.
That's not the only reason. That's a necessary condition. If you didn't have, so to see any effect of quantum mechanics, if A1 and A2 and B1 and B2 are all simultaneously diagonalizable, then you wouldn't see any effect of quantum mechanics at all, right? So I was just trying to explain why the classical reasoning that we gave previously went wrong. And the point about A1, A2 and B1, B2 not commuting is the fact that quantum effects are important in system A and quantum effects are important in system B. But just them not commuting doesn't mean that CAB will have to be 2 root 2. CAB could be 0 even if A and B don't commute. So the fact that they are entangled is a statement also about a state. It's not just that, if they don't commute, automatically CAB becomes larger than 2. The fact that they don't commute is important because if they did commute, then it would just reduce to the classical situation. So the fact that entanglement is a quantum property, and that's the fact that A1 and A2 don't commute. But it's in addition, when you say two systems are entangled, this is a statement about the state. So there's some joint state of A1 and A2, and so just having them not commute is not sufficient. There's some property of the joint state, and that is what we are referring to when we say the two systems are entangled. Okay, let me just try and explain why, how you could saturate this bound. It's actually quite easy to see. So say we have so we were just referring to joint state. So say we have a joint state psi. Okay, we could even have some big system. In principle, psi could be a black hole state, and A1, A2, B1, B2 could be some field operators we are measuring somewhere. Once we've normalized them correctly to make sure the eigenvalues are not larger than 1. Okay? So say we have some joint state of this kind psi, then we could very easily see how you saturate Cytosins bound, and that's in the following way. Remember, the state psi is a vector. It's a vector. Okay, it's not a number. And similarly, you can act on the state psi with A1, A2, B1, and B2, and you will get additional vectors. Okay, so let me use the notation, which is that A1 is A1 psi. Actually, let me put an I here to avoid having to write, and Bi is Bi psi. Okay, so the action of A1 and A2 on psi gives you these vectors, which I'm denoting by A1 and A2, like ket A1 and ket A2. And the action of B1 and B2 on psi gives you vectors, which I'm denoting by ket B1 and ket B2. And then notice here is a very simple way in which you can make, you can saturate this bound. Okay. Oops. So let's say this is the vector A1, this is the vector B1, this is the vector A2, and this is the vector B2. Okay? And all these angles are 45 degrees. Okay? So this is 45 degrees and this is 45 degrees. If this is the case, you can check, and all vectors are length 1. They're length 1 because to start with, the state psi was normalized, so it had length 1. And if you act on it with some operator A, you can't get some vector that's larger than length 1 because the operator norm of A is bounded by 1. You could get something that's smaller than 1, but then you wouldn't be saturating Cytosins bound. To saturate this bound, you need to act on it and get a vector which is of length 1. And the main point to note here is that if you take B1 plus B2, just by the right angle theorem, this is square root 2 of A1. And similarly, B1 minus B2 is square root 2 of A2. Okay, these are vectors in a complex Hilbert space, but I'm just, you can always choose some situation where all the vectors are real, which is what I've plotted. And it's very clear just from here that if you were to look at the expectation value of CAB, that this is 2 root 2, right? And that's because the expectation value of CAB is nothing but the A1 into B1 plus B2 plus A2 into B1 minus B2, right? And when you do that, it's clear that because B1 plus B2 is square root 2 into A1 and B1 minus B2 is square root 2 into A2, and because A1 itself has length 1, this whole thing is just 2 square root 2. Okay. So this is one example of how you can saturate the bound in quantum mechanics. And once again, you see here that there's no sense, the fact that these vectors are not, B1 and B2 are these vectors which are orthogonal to each other, is what is telling you that, you can't assign some simultaneous value to B1. You can't assign simultaneous real numbers to B1 and B2. And that is what we did to derive the classical bound. And you can see here in quantum mechanics how it can be violated. Okay. I said something about the commutators being required. In fact, you can check in a simple case. Let's say you take a very simple case, which is say A1 squared is A2 squared, which is B1 squared, and B2 squared is 1. Okay. This is an additional assumption. This was not required for what we did. I'm just making this assumption to make the algebra simple. Then you can check that CAB squared, where CAB was the operator I defined. If you just go through some algebra, you will find that it becomes 4 minus A1 commutator A2, B1 commutator B2. Okay. So the fact that this CAB squared can become as large as 8 is because you have a contribution from these non-zero commutators. And if A1 and A2 commuted and B1 and B2 commuted, there was no way you would get a value of CAB larger than 4, which is the classical case. Of course, it could still be that the expectation value of this term is 0 in a given state, and then you would still not have a large value for CAB. But it's the fact that this value could, in principle, raise the value of CAB squared to 8, which is what allows you to have these correlators which exceed classical correlators. Okay, so this is a pretty simple notion of entanglement. It's a useful technical thing which we'll use several times, and I think it's slightly more tractable technically than the entanglement entropy. Are there any questions about this result? I now want to explain in what sense entanglement is monogamous when you use Bell's inequalities.
So I have a question.
Yeah, go on. Yeah.
Does this violation of Cytosins bound also measure the degree of entanglement? I mean,
yeah.
Okay.
Yeah, it's not a violation. Cytosins. So we talk about violations of Bell's inequalities. You'd never violate Cytosins bound in quantum mechanics. Cytosins bound is the 2 root 2. So that you never violate. But we could speak of violations of Bell's inequalities, and you could say that something which is larger than 2 is a violation of Bell's inequalities. And yes, this is a quantitative measure of entanglement. In that this CAB is how much larger it is than 2 is telling you in some sense how entangled these systems A and B are. In principle, if you took like a system, a big system which had many degrees of freedom and another system which had many degrees of freedom, really, if you wanted to measure entanglement, which is the kind of thing that the entanglement entropy measures for you, you would need to count how many such entangled subsystems can you extract. So how many Bell pairs can you extract? So that's what the entanglement entropy tries to measure. But if you have like one qubit on one side and another qubit on the other side, then indeed this expectation of CAB is giving you a quantitative measure of the degree of entanglement. Okay.
Yeah.
Yeah. Is there another question?
I have a question. I think it's a quick one. I mean, if I can.
Sure.
So the plot that we with the vectors that we drew before, that's just to be sure that this is just a specific case, right? It's not like anything we said implies that the vectors are in these directions.
Yeah, indeed, that's correct. This is just a specific case.
Okay, perfect. Thank you.
In principle, notice all these vectors are real, which is why I drew them on a two-dimensional plane. You didn't have to have that situation. So it's a very simple situation. You have only 4 vectors, and so you could try and choose some basis to make these vectors work this way, but you could have something slightly more general even then.
Okay, Suvrat, there was one more question in the chat. I think when you defined operator norms, it's about that slide, and the question is: are these operator norms Frobenius norms?
The operator norms I just mean the largest eigenvalue. It's just the fact that if you take a vector of unit length, how much can the action of the operator stretch it? So it's just like the maximum value of mod of a psi when psi is a unit vector.
Okay,
I mean, these are Hermitian observables, so this is just just the largest eigenvalue also. Okay, good. So now I want to describe what one means by the monogamy of entanglement. Okay. So to look at the monogamy of entanglement, say we have a third system C. Okay. So now we already had these systems A and B, and say we have a third system which is C. And what do we mean by saying that C is a third system? It's a distinct system. We mean the fact that CIAJ is equal to CIBJ, and this is 0. Okay, so CIAJ is CIBJ, and so C commutes with the observables in A and also the observables in B. Okay, so this is what it means precisely that C is probing a third system. It means that it commutes with the first 2 observables that we have. And of course, if you have such a system, then you can define an observable which you can call CAC, which is A1 into C1 plus C2 plus A2 into C1 minus C2. Right? And you can use this to ask how much entanglement is there between A and C. And that, it works the same way. Once again, this entanglement is bounded by 2√2. And, if it's less than 2, that tells you that systems are in the classical, correlators are just classical correlators. Okay? So the only way we say A and C are entangled is if the correlators between A and C are between 2 and 2√2. Okay? Then it turns out there is a very nice proof. There's I think it's quite remarkable, at least. There's a remarkable inequality. And I have to say, I find this inequality an extremely nice measure of monogamy of entanglement. There's so many quantum information measures people discuss, and many quantum information measures have associated notions of monogamy. The entanglement entropy also does. But the inequality we'll write down now, I think, is very pretty. And it tells you something very nice. It just tells you that CAB squared plus CAC squared is smaller than or equal to 8. Okay, that's it. Now, if you think about this for a minute, you will see it's immediately telling you that entanglement is monogamous. Okay, so just to belabor the obvious, if it is true, if mod of CAB, mod of the expectation value of CAB is larger than or equal to 2, this just implies that the mod of CAC is smaller than or equal to 2. Okay, and obviously the converse is also true. Actually, let me put larger here and smaller here. We don't need equal to. This is larger than 2. This is smaller than 2. And obviously, this is also true. If this is true, larger than 2, then this means that CAB is smaller than 2. Okay. So if it is the case that A and B are entangled, then A and C cannot be entangled. Then A and C, the correlators between A and C have to be below the classical bound. So you can always have classical correlators, right? Classical correlations can be shared. I mean, that is the principle of the monogamy of entanglement. When the classical correlations can be shared, you can always have, one operator A, which has classical correlators with another operator say everything is just one together, all A1 and A2 and all of them are just one together, then clearly, it's always the case that CAB is 2, CAC is 2, everything is just 2 because all operators are just 1. No operator ever takes, A1, B1 is 1, B2 is 1, they're just constant operators. And that's a classical correlator, right? Because, you don't have any randomness at all. And these classical correlators can be shared amongst an arbitrary number of parties, but quantum correlators cannot be shared. Okay? So this beautiful inequality tells us that classical correlators can be shared, but quantum correlators cannot. Okay, so this is a very nice inequality, and it's a very short statement of the monogamy of entanglement, very short and very simple statement of the monogamy of entanglement. Is there a question?
Yeah, just a quick question. Can you repeat what you mean by a correlator to be shared?
Yeah, sorry. So I just mean that yeah, sorry. I mean that. Well, okay. I just meant that if A is correlated with B, A can also be correlated with C if those correlations are just classical correlations. But if A has some quantum mechanical correlators with B, like some correlators which exceed the maximal allowed classical correlators, A cannot also have quantum mechanical correlators with C. Actually, this is an imprecise statement. This is not like a precise statement. Okay? This statement is simply saying that if the correlators of A and B exceed the maximal classical limit, then the correlators of A with nothing else in the world can exceed the maximal classical limit. A can only have classical correlations with something else. A cannot have joint quantum correlators with more than one system. Okay, that's all we're saying here. I hope that's clear. Maybe the statement is slightly imprecise.
Yeah, it's clear. Thank you.
Yeah. Okay. So notice that this is true for. Yeah. Is there another question?
Yes. Sorry. This property is symmetric under A and B. For instance, if I exchange the A and B, this is also correct. I can say same situation.
Correct. So there is a similar entanglement. I mean, CAB is just symmetric, but it's also true that CAB squared plus CBC squared is also smaller than 8. So instead of B can also not be entangled, of course, with if B is entangled with A, it cannot be entangled with C. So okay. CAB is just symmetric. CAB is measuring like some correlators between A and B. And it's true that if A and B have correlators which exceed the classical limit, then A cannot have such correlators with anything else in the universe. And similarly for B, if B has correlators with A, cannot have correlators with anything else in the universe. Okay, so this is the sense in which entanglement is monogamous. You can have one entangled partner. You can't have multiple entangled partners. Each system can be entangled with one other system of this kind. It can't be entangled with multiple other systems, provided these C commutes with B and A. Okay? So that's the sense in which entanglement is monogamous.
Okay, so but it is, okay. Sorry. Please go on. Yeah.
But this is true for maximum entanglement.
No, it is true for any entanglement. Notice that if AB is larger than 2, that is entanglement. Okay, so by our definition of entanglement was if CAB is larger than 2. So if CAB is larger than 2, CAC has to be smaller than 2. Okay, so yes. Even if you have less than maximal entanglement, you might have thought maybe I'll make CAB 2.1 and CAC 2.1. But that won't work because 2.1 square plus 2.1 square is 4 square plus, is larger than 8. So it's not just for, it's not if A and B are maximally entangled and A cannot be entangled with C. If A and B are entangled at all in the definition that we gave in that CAB is larger than 2, then A and nothing else can be entangled. Okay, so it's not just for maximal entanglement. It's for any entanglement defined in the sense that we did.
Thank you very much.
Okay.
Sorry, I also have a question.
Yeah.
This result only works for bipartite entanglement, right? So yes. I cannot understand this result in terms of multipartite, genuinely multipartite entanglement.
Sure. I mean, there's a lot of work on entanglement, and there are many questions we could ask. But this is all we will need for what we are doing. We only want to look at like bipartite entanglement between systems and pairs. You could ask other questions about higher things, which I'm actually not even an expert on. I'm just trying to develop what we will need for the black hole information and to make the paradox precise. I mean, I should say, of course, there's an enormous amount of literature on measures of entanglement and how it can be done, and I'm sure there are people who are hearing who have much more knowledge about this. But this is just a very simple and beautiful result that is all we will need in our discussion of black hole information. And you're right, it doesn't measure multipartite entanglement. It's just measuring, you have the system A and B and A and C, and you're measuring pairwise entanglement in each case.
Okay, Suvrat, there are a couple of questions. The first question is, if A and B are quantum correlated, it is actually lowering the classical bound for A and C correlator also.
It's not lowering the classical bound, it's lowering the possible correlations you can have for A and C. Yeah, it's true that, you know, if A and B have some correlators which are 2 root, yeah, good. So this is true that, you know, if A and B are correlated and that CAB squared is 2 root 2, then indeed it tells you that CAC has to be 0. That's a good point. You know, if, so if CAB, for instance, is 2 root 2, then CAB square is already 8, and then A cannot have any correlations with C at all. So, and that's true.
Okay, then I think one question you've already answered. Isn't maximum entanglement monogamous?
Yeah, it's more than that. It's stronger than that. I mean, of course, if CAB square is 2, then it's stronger than CAC is just 0.
Right, okay. And I think the final question is, can we use definitions other than CHSH to measure entanglement? And why is this special?
I mean, yeah, that's what I said. I mean, as I said, of course, there is a virtually infinite number of notions of how to define entanglement, and many notions of entanglement have an associated notion of monogamy. The original formulation of these paradoxes we are trying to reach to, in fact, was in terms of entanglement entropy, which is another way of measuring entanglement if you have a pure state between two systems, to measure the entanglement between them. And so there are many, many ways of measuring entanglement. I mean, this is not unique. As I said, the advantage of this measure that we're looking at is that it's a measure in terms of 2-point functions. When we later write down things, these A1s and A2s and B1s and B2s are just going to be some simple operators we can write down. And this is just a 2-point correlator, so it can be computed reliably within perturbation theory without having to worry about any subtleties. That's the reason why I'm focusing on Bell correlators, because later we will make some statements, and it's important for us to be able to focus on the physics of what's happening rather than having to worry about the subtleties of how to compute various quantities. You know, as I said, you could use different measures of entanglement like the entanglement entropy, but then, you know, we would end up getting into a discussion of, you know, what about the UV divergences and what happens to them, and how do you regulate them, how do you define it in gravity. But these operators that we are going to use are going to be well defined in gravity as well, because these A1s and B1s and C1s and C2s will just be some simple operators in field theory, which we can just write down. And that's the reason I'm focusing on these measures of entanglement and these Bell correlators. Okay, great. So now I want to move on to a different topic slightly. So this is a notion of entanglement and the sense in which entanglement is monogamous. I now want to ask a slightly different question, which is about the average entanglement between subsystems. Okay. And at the end of hopefully this lecture, we will arrive at the page curve, which is also a measure of average entanglement between subsystems, although it uses the entanglement entropy. I'm first going to describe this notion of average entanglement using these CHSH correlators, but then we'll go on and describe it using the entanglement entropy. Okay, so the question we want to ask is the following. Okay, we want to say that let us say it is we have two systems. So say we have two systems. One is of size e to the s prime, and actually say we have one big system, okay? And we divide it into two parts, and the other is of size e to the s. Okay, so there's one system, one subsystem as part of a big. So the big system has a Hilbert space which has dimension e to the s plus s prime, and one system has dimension e to the s prime, and the other system has dimension e to the s. So these are subsystems of some big system. Okay? And we will assume for simplicity that e to the s prime is much smaller than e to the s. Okay? This actually is not a very strong assumption. You might think that this is saying that one system is much smaller than the other system. But in fact, this assumption that e to the s prime is smaller than e to the s, which will make our life simpler, we don't actually have to make this assumption, but it will make our life simpler, is not a strong assumption for the following reason. We are going to examine systems like black holes, which have a lot of entropy, right? Which are like systems which are in the thermodynamic limit. So say, the big system, or say, one system has 10 to the 10 qubits, right? And so its entropy actually, so S is 10 to the 10. Remember, S itself is large. So e to the S is exponential of this. It's 2 to the 10 to the 10. Okay, and the other system has almost 10 to the 10, but 1/millionth less than that, right? So you see that S prime by S, the ratio of S prime by S is almost 1, but e to the S prime is much, much, much smaller than e to the S. Okay, so e to the S prime in this situation, so S is 10 to the 10. I mean, S is not actually 10 to the 10 to the factor of log 2, but I'm going to ignore that. And here S prime is 1 minus 10 to the minus 6 into 10 to the 10. And you see it's true that e to the S prime is much smaller than e to the S. Okay, and all we need is that S minus S prime is much larger than 1. We don't actually need S prime divided by S to be much larger than 1. Okay, so there's this approximation that we are going to make, and we will carry it through the rest of this lecture and actually later in the course as well. But I want to emphasize it's not a very strong approximation, because if you have a huge system and you divide it into two parts, it's almost the case, unless you divide it exactly down the middle, that one part has much smaller, dimension of the Hilbert space than the other part. The two parts might have comparable entropy. In this case, the entropy in one sense is comparable in that S prime is almost the same as S up to a factor of 1 in a million. But the dimension of the Hilbert space, which is the exponential of that, is much smaller, and that's the assumption that we're going to need. Okay, good. So now we want to say in some precise sense, we want to ask, in what sense, if you take a typical state of the large system, in what sense the systems are entangled. So the question is, take a typical state of the large system, okay, and how are the subsystems entangled? So that is the question that we want to ask. Okay, so we'll give two answers to this question. One answer is going to be in terms of these Chsh correlators that we described, and the other answer is going to be in terms of the entanglement entropy. But both the answers basically rely on trying to understand the density matrix when you have this big system which you've divided up into two subsystems. In this line that I have written here, we have the phrase typical state, but in fact, we spent just a couple of lectures earlier a lot of time discussing what one means by typical state. So typical state, once again, means take the Haar measure on the big system, which we wrote down. So take the Haar measure on the big system, and then ask, compute some quantity and ask what is the average of that quantity with respect to the Haar measure in the big system. So once again, typical state means precisely what we said before. Said more physically, you have a big system, it's prepared in some way, it's in a pure state, you don't know what it is, but it's in some pure state. You go pick it up and you ask, what is the most probable value for the quantities I'm going to measure, including for measures of entanglement between these two subsystems. Okay, so that's the sense in which we mean typical. It means precisely what we used a couple of lectures earlier. Okay, so I want to first make the following claim. As I said, we'll have two measures, and the two measures will be that if you are given some operators which satisfy some simple properties, which I'll make precise in a second, okay, in smaller subsystem, then we can locate some operators in the larger subsystem to saturate Cytosins bound. So it doesn't, we're going to ask for some operators, and these operators are going to satisfy some properties. We're not going to say anything about the state. These operators are going to be basically, the properties they're going to satisfy is they're going to behave like sigma z and sigma x. So they're going to behave like some qubit operators. And we're going to say in any typical state, you can always find operators in the larger subsystem. So, we have a smaller subsystem, which is one part, the part on the left. We have a larger subsystem, which is the part on the right. And we're going to say, you give me any operators in the smaller subsystem, and I will find for you operators in the larger subsystem, so that when you put these two operators together, A and B together, you will be able to saturate Cytosins bound. Okay, so it's a strong statement. This is a statement in some sense of maximal entanglement between the two systems, because it's saying you pick up any, you have a system, you had, as we said, you could have in one system like 1 minus 10 to the minus 6 into 10 to the 10 qubits, and you could pick up any qubit. Just pick up any qubit. And where is its partner? Remember, we said it has to have one partner in the world with which it is maximally entangled, and that partner happens to be in the other system. Okay? And the only assumption is that the whole system together is in a pure state. And if that's the case, you pick up any qubit on one side, its partner is on the other side, and this partner saturates the Cytosins bound in that it's maximally entangled. Okay? So this statement is a powerful statement, and even though it looks like a simple statement, it's actually telling you about maximal entanglement between the two subsystems. And the second thing we will argue is that the entanglement entropy between the two systems, between the subsystems, okay, obeys a page curve. I have to explain what the curve is with respect to. Right now, it's not clear what we're going to draw the curve with, but I'll explain what the curve is with respect to and what that means, what a page curve means. Okay. So before that, let me try and prove first property A, and then I will go on to property B. Okay. So let's start with property A. As I said, we have to consider a typical state in the system, and the typical state we can write in the following way. We pick a basis for the smaller system. We pick a basis for the bigger system. So in one case, I sum from 1 to e to the s prime. In the other case, I sum from 1 to e to the s. So n is the basis for the larger subsystem. M is the basis for the smaller subsystem. And this is a typical state. This is some state in the big system. And I write down the usual measure. Okay, so we wrote down this measure already. But this measure is just going to be product over d2 amn, and it's going to be delta of sum of mod of amn squared minus 1. Okay, so we already wrote down this measure. I'm not actually going to do too much with this measure explicitly, although we will quote some results about expectation values under this measure. So the question is, you want to compute some correlators, and then with respect to this measure, which is the Haar measure that we discussed in great length a couple of lectures earlier. Okay, so first, if you have a state of this kind, for any state, for any assignment of the values A, these coefficients A, you can ask what the density matrix is. Okay, so the density matrix of the smaller subsystem is rho m prime. Remember, the density matrix has is an e to the s prime times e to the s prime matrix, and so when I'm using m, I'm using it for the smaller subsystem. And how do you do it? You just sum, right? You just take this amn, you take a star m prime n, and you sum over n equal to 1 to e to the s. Okay, so you just take psi and you trace over the bigger system, and if you do that, you'll get a density matrix for the smaller system, right? So we want to ask first about some simple properties of the density matrix for this smaller system. Let me first emphasize that we're talking about the density matrix of the smaller system, but I want to emphasize that the eigenvalues of the larger density matrix are the same. So, the larger density matrix is not the same as the smaller density matrix, because, these are density matrices in different Hilbert spaces. One is in an e to the s times e to the s dimensional space. The other is in e to the s prime times e to the s prime dimensional space. But there is a sense in which these density matrices are very similar, and that is that they have the same eigenvalues. Okay, and this is under the assumption that the full state of the system is pure. Why is this the case? And that is because one can always, let's say someone gives you some coefficients AMN, right? Someone gives you some state which is AMN into M times N. And this is, gives you some particular entanglement structure between the smaller system and the bigger system. Then one can always choose a basis to diagonalize. Okay, actually diagonalize, this AMN is actually a rectangular matrix. So in fact, the more precise word is that you should do a singular value decomposition. You shouldn't diagonalize. And what it means to do a singular value decomposition is that you make a change of basis both in the smaller system and in the bigger system in such a way that AMN, only the diagonal elements of AMN are non-zero and all other terms are zero. Of course, this is a rectangular matrix, so it's not really, when we say diagonal elements, what we mean is that, AMN is only zero when M is equal to N, but there are of course many other terms in a larger block which is set to zero. But the statement is that if you do the singular value decomposition, you can always write this state psi in the following form. Okay? You can always write it in this form by making some change of basis both in the smaller system and in the larger system. And this is now a form which is just diagonal, and notice the sum is only over a single index, over this index alpha. Okay? You're not summing any more over M and N. And of course, this index alpha cannot go any larger than e to the s prime because the smaller system doesn't have any more elements in its basis than e to the s prime elements. And so it tells you that the rank of the larger density matrix can also at most be e to the s. It could be smaller, but it can't be any larger than e to the s prime. Okay? And this tells you the fact that you can rewrite the state in this way, which follows just by doing a singular value decomposition of this AMN, tells you that, if in this basis it's manifest that the density matrix for both the subsystems is of the kind rho alpha times alpha alpha, and the larger density matrix clearly has a lot of zero eigenvalues. But the non-zero eigenvalues are the same as those of the smaller density matrix. Okay, so we are going to keep referring to the density matrix of the smaller system, but I want you to remember that everything we say about the eigenvalues is also true for the density matrix of the larger system, which has the same eigenvalues. If I was not clear about this, I'm happy to take questions at this point about this issue. I don't see any questions in the chat, so maybe people are familiar with this. Is there a question?
I had one question. How different is this from spectral decomposition?
From what decomposition?
Spectral decomposition. I mean, if alpha is the eigenbasis of the larger Hamiltonian, then also one can write this psi in that form.
There's no Hamiltonian here. These are here we're just talking about kinematical properties. So this is just a statement that if I take some rectangular matrix, 1, 2, 3, maybe 3, 2, 4, 5, I can make I can make a unitary transformation by multiplying it with one matrix on the left, a unitary matrix on the left, and another unitary matrix on the right, so that I can turn it into something which has some non-zero elements here and here and has zero everywhere else. Okay, that's all we're saying. So that's all that is being said here. There's nothing very deep being said here.
Okay, thanks.
Okay, so very good. So I just wanted to say this is the sense in which the larger density matrix is also like the smaller density matrix. So the first question we can ask is, what is the expectation value of rho m prime? Okay, and remember this is with respect to the Haar measure, which we wrote down. Okay, so the expectation value of rho m, this is obviously just you have to do this integral m prime n, and you have to do this integral with this measure that we had previously. But we know what this integral gives you, right? This integral we know clicks only when m is equal to n, when m is equal to m prime and n is equal to n. Now n here has been set by force, because we are summing over n being equal to itself. But when it clicks, it gives you a value, but that value is set by the dimension of the big Hilbert space. So this is just e to the s plus s prime. Okay? And then we have a sum over n, and the sum is over delta mm prime, and then there's a delta over nn. Okay? And when you sum over n, this sum over n of this delta function is just going to give you e to the s on top. So I can erase this, and I can just write an e to the s here. And then I can cancel 1 e to the s. And therefore, I find that the expectation value of the density matrix is just 1 over e to the s prime into delta mm prime. Okay? So the expected value for the density matrix is the identity matrix in the smaller system. Okay? Is this clear? The expected value for delta mm prime is that for all the off diagonal elements, the expected value is 0. And for the diagonal elements, the expected value is 1 over e to the s prime. So this is the identity matrix. It doesn't even depend on what basis you chose. It's just the identity matrix that you expect for the smaller system. And remember, this identity matrix is obtained because, as I just emphasized, we don't have any Hamiltonian, and we are summing over all possible states in the bigger system. And if you do that, you expect the density matrix of the smaller system to just be 1 over e to the s prime times delta mm prime. The fact that you have a 1 over e to the s prime is necessary because the density matrix has to be normalized. Okay, but you might say, you told me about this expectation value, but this expectation value, doesn't, maybe there are big fluctuations about the identity. It's never good to talk about the expectation value, and therefore there's a more useful thing we could ask, and that useful thing we could ask is, what is the deviation of the average eigenvalue from the identity matrix? And so you could ask a question of this kind, which is trace of rho mm prime minus e to the s prime into the identity matrix, trace of this the whole squared. And you could ask, what is this quantity if you sum over m and m prime? Okay? Now there's a simple computation that one can do for this. Actually, in the lecture notes, which I'll upload, the computation is done. So you just have to compute once again the expectation value. Notice that when you compute the square of the expectation value of this rho mm prime, you'll get a square of 4 of these coefficients. You'll get a, m, n, a, m prime, and then conjugate of a star, m, and some other n index. And so you just have to compute an expectation value of 4 of these. This is actually quite similar to the calculation that we did earlier as well. And I won't do it, but you can check the notes, so you can try and do it yourself. I'll just quote the result. And the result is that this turns out to be e to the s plus e to the s prime by e to the s plus s prime plus 1 minus 1 by e to the s prime. Okay, and there's some simple thing you can do. But this is actually the sum. So, if rho mm prime had different eigenvalues, what this is telling you is, you take the eigenvalues, you subtract off the identity matrix, and you sum over all of them. But we want a good notion of what the average deviation is. To get a good notion of what the average deviation is, you should divide this by an additional factor of e to the s prime, because there are e to the s prime such eigenvalues. So I should divide this by an additional factor of e to the s prime. Okay. Now, if I do this, you can check very simply by just simplifying the expression that at large s and s prime, let's say we call this delta. This delta is approximately 1 by e to the s plus s prime. Why is that the case? Because you take e to the s prime, put it up in the numerator, you get an e to the s plus s prime from the term on the left, but you have to subtract off a minus e to the s plus s prime. So notice the e to the s plus s prime terms cancel. You are left with an e to the 2s prime, but there's also an e to the 2s prime in the denominator, and therefore you see, if you neglect some terms of 1, that this delta is of size e to the s plus s prime. And this delta is telling you about the average deviation squared of each eigenvalue from 1 over e to the s prime. Okay. But notice that this average deviation squared is actually, so square root delta is the size of the average deviation of the eigenvalues, right? But square root delta is just 1 by e to the s plus s prime by 2. Okay? And this square root delta is much smaller than 1 over e to the s prime. Because remember, s is much larger than s prime. And therefore, e to the s is much larger than e to the s prime, which is the approximation we said in the beginning. And therefore, the square root delta is much smaller than 1 over e to the s prime. And therefore, the average deviation of each eigenvalue is smaller than the expectation of the eigenvalue. So remember, the expectation of the eigenvalue is 1 over e to the s prime. And the average deviation we are finding is much smaller than that expectation. And that tells you that it is indeed the case that the density matrix is close to the identity matrix, because not only is it that the expectation value of the eigenvalues is 1, the average deviation is suppressed by this factor of 1 over e to the s minus s prime, which we already assumed was something that was very large. Okay? So this tells us that the average density matrix is close to the identity, and by average, the average density matrix. Okay? And by average, once again, we mean average by taking a typical state in the larger system. And we've not only, the average density matrix, if you just take the average, really is the identity matrix. Of course, this identity is correctly normalized. But it's not only that, it's the fact that the fluctuations of the density matrix of the smaller system are also small compared to the larger system. Notice, by the way, that this does not work if you try to use this argument for the larger system. It would not work. It would not work because remember, it's not the case that the larger subsystem has a density matrix which looks like an identity in the larger system. The identity in the larger system is 1 over e to the s times delta n prime. And it's, that's not, clearly that cannot be correct, because remember, we emphasized that the rank of the larger density matrix was the same as, could not be any larger than e to the s prime. And therefore you don't expect, and you can see from here that in this case, you will find that the fluctuations are larger than e to the s. They're not smaller than e to the s. And so it's not true that the density matrix of the larger subsystem is expected to be the identity in the larger subsystem. But it is true even there that the eigenvalues of that density matrix are expected to be 1 over e to the s prime, which you can see by looking at the smaller density matrix. Okay. Are there any questions about this part? I now want to derive in the last 10 or 15 minutes some quick results from the fact that the average density matrix is close to the identity. In fact, I'm now not even going to keep track of corrections. I'll just assume that the density matrix is the identity, and then we'll derive some simple results.
Okay, there's one question in the chat. Yeah, he's asking, are the higher moments of the deviation about maximally mixed state also similarly suppressed?
So you could compute higher moments indeed, and the higher moments would also be suppressed. So if you look at Page's paper, so this result I wrote down was actually first derived by Lubkin, but Page quotes the result, and Page also has results for the higher moments which you can look at. So they're also small, correct? Which I have not quoted for. Page's paper is called the average entropy of a subsystem. You'll easily find it, and you can check that the high, you can check also about higher moments. Are there other questions? Okay, good. So now let me just say that so we choose some basis. Let's now choose a Smith basis for the state of the bigger system. And once we choose the Smith basis, what we said is we can always choose the Smith basis so that the state now looks like this. So this is the concrete outcome that we get from this computation of the density matrix. It's the fact that you can, we're saying that you can write the state in this way. And that's because the eigenvalue, the coefficients that appear in the Smith basis are the square root of the eigenvalues of the density matrix, which we have argued are close to e to the s prime. And therefore, it tells us we should be able to write the state in this way. Of course, I emphasize it's not the case that all states can be written in this way. And in writing the state this way, I have also made a choice of basis. So this m may not be, the basis you started with, you may need to make a basis transformation to get the state to this form. But the point is that, many states, if you try and do a Smith decomposition, you should be able to write states in this form. And of course, that's not true for all states. But this is the assumption that is simple for us to go forward because it's the statement about a typical state. Okay. So now let's say we have the state, and say we have some pseudo spin operators in the smaller subsystem. Okay. What does it mean that we have pseudo spin operators? What we mean by these pseudo spin operators is that these operators should behave like sigma z and sigma x, in that we want some operators with square to 1. Okay. And what is more, we also want this, we want that if you add them and square them, or if you subtract them and square them, you get 2. So if you can check that, sigma z and sigma x have this property. And if you have a big system, you can always find operators that have this property. This just means, when we are focusing on pseudo-spin operators, this is just a precise way of saying, we are focusing on 1 qubit degree of freedom. So you might have a big system, but you can always locate operators which satisfy this property. And this is our way of saying that you focus on a qubit. In fact, we will find later you can also locate such operators in a quantum field theory. So even in a quantum field theory, it's not hard to isolate one. A quantum field has an infinite number of degrees of freedom, but you can always isolate a qubit degree of freedom, and that's what we have done here. Okay. So we can find we can find such operators in QFT as well. These are not like only qubit operators, and in fact later we will find such operators in a QFT. But anyway, these are operators which have this property that we want, and this is in the sense that they mimic sigma z and sigma x, and they could be something complicated made of the field and its conjugate momentum, but they mimic sigma z and sigma x in this form. Okay. So now what the result I claimed in the beginning was that if you're given some operators which have some properties, this is now I've now specified what the property I want is. Then the result I claimed in the beginning was that you could always find operators in the larger system so that you would saturate Cytosins bound with this A1 and A2 operators. Okay. So now let me now show that. So we have this state, and let's define now in this basis that we have chosen the matrix elements of the state. So this is a specific basis. This is the basis that appears in the Smith decomposition. Okay. So it's a specific basis. It's not just some random basis. It's a specific basis. It's a basis in which I wrote the state here. Okay. So this is the same basis that I have here, that I have on the next slide. And let's say we have some basis elements, and the basis elements look like this. I should make sure I have my notation correct. MQ times Q. Okay. And similarly for A2. Okay. So this is just, this is just notation. Now, the point about finding operators that are entangled with these A1 and A2 operators is that if you're given these operators, you can define another operator. So you can define this operator, which I'll call A1 tilde, which has the property that it acts in the larger system. So this operator acts in the larger subsystem. And this M tilde is what appeared here. Okay. It's this basis that appeared in the basis for the larger system here. And it's this same M tilde that is appearing here. Okay. So we define an operator which has the property that its basis elements are just the transpose of the basis elements that appear on top. Okay. So compare this with this. I've done nothing. I've just transposed them. Okay. So on both sides you have M and M tilde, And what I've done here is I've taken a matrix in the larger system that in this Smith basis has matrix elements which are the transpose of the matrix elements of the original system, of the original operator that I found. Okay. And similarly, we can define an A tilde which has the same property. Okay. An A2 tilde. Okay. Now, because the matrix elements of A1 tilde and A2 tilde are the same as the matrix elements of A1 and A2, it is clear that the operator norm of A1 tilde and the operator norm of A2 tilde is also 1, right? And it must be the case because the matrix elements of A1 tilde and A2 tilde are just the transpose of the matrix elements of A1 and A2. And we already said that A1 and A2 were these pseudo-spin operators which squared to 1. So they had eigenvalue which was either 1 or -1. And therefore, A1 tilde must have the same property. That it also has, it also has maximum operator norm, which is 1. And in addition, it must also be the case that A1 tilde and A2 tilde themselves behave like pseudo spin operators, which you can check, which follows simply from the fact that the matrix elements are the same as the matrix elements of A1 and A2. But there's an additional interesting property of these A1 tildes and A2 tildes. And that additional interesting property is you can ask, what is the action of A1 tilde on the state psi? And you can check that this action, you just put in the state psi, okay, is just given by 1 to Q to S prime into A1 tilde on M tilde. It's just a linear action. Okay? And this is just 1 over e to the S prime by 2. You just use the definition that I had previously. And now you're summing over M and Q. And you find that this is A1 QM into MQ tilde. And then you just rename Q and M. Okay. So this just becomes 1 over e to the S prime by 2 into A1 MQ, okay, into QM tilde. Okay. And this, you notice, is exactly what we call A1 psi. So the result we want is actually the one that tells you that A1 tilde on psi is the same as A1 on psi. And that's because we defined A1 tilde in a particular way. Let me emphasize that, A1 tilde was defined after you gave me a Smith basis. So for a given state, you give me a state, you give me some operators A1, and then I can locate for you some operators A1 tilde in the larger subsystem that have the property that when the systems are maximally entangled, as they are here, when, in the Smith basis, the eigenvalues look like e to the S prime by 2, the action of A1 tilde on psi is the same as the action of A1 on psi, even though the operator norm of A1 tilde and A2 tilde is 1. Okay. It was important that in all of this, I didn't have to worry about this e to the S prime by 2 at all. If I had to worry about like different coefficients appearing in front of M and M tilde, this manipulation would not have gone through. This manipulation has gone through because the coefficients that appear here always look like e to the S prime by 2. Now, with this the case, let's just define some operators. So similarly, we'll also find that A2 tilde on psi is A2 psi. Okay? And then we can just define B1. So just to go back to the notation we had previously as being A1 tilde plus A2 tilde and B2 to be 1 by square root 2 into A1 tilde minus A2 tilde. And it's clear that because A1 tilde plus A2 tilde also squares to 2, the operator norm of B1 and B2 is also 1. So B1 square is 1 and B2 square is 1, which is clear. And then look at CAB, which is defined precisely as we defined it previously. Right? Now, this is some operator, but let's compute the expectation value in this state psi of CAB. This expectation value is obviously just square root 2 into, notice that B1 plus B2, when you add these two, the A2 cancels. And so you just get A1 tilde. And from here, you just get A2 tilde, right? So if you just compute the expectation value, you get twice of A1 tilde, one factor of square root 2 cancels. And therefore, you just get from here psi into A1 squared psi plus square root 2 into psi into A2 squared psi, and this is just manifestly 2 square root 2. Okay. So I just want to emphasize, we did some manipulations, and the manipulations, it might almost have looked that, we were doing something kind of meaningless. We were doing these manipulations and taking these transposes and so on. But in fact, the result we have is a nice result, and it would not have been true unless these systems were maximally entangled. Just to take a step back, what we have argued here is that we have a big system, which is in the thermodynamic limit. You divide it into two parts. Almost any way you have of dividing the system into two parts ensures that the dimension of one part is much larger than the dimension of the other part. Under this assumption, we proved that the density matrix of the smaller part was close to the identity, and therefore, if you chose a Smith basis for the big state, you could write it as 1 over e to the s prime by 2 times some entangled state. And then we said, well, if you choose any set of operators, we didn't put any restriction on what the operators in the first system were. You just focus on one qubit. You could focus on any qubit, right? So just choose any qubit you like, and just choose some operators that are qubit-like operators in that they behave like spin operators. I will find for you a partner set of operators in the bigger subsystem so that the two sets of operators in the smaller and the bigger subsystem are maximally entangled. Okay? And this is true for any typical state that you pick up from the bigger system. Okay, so this is actually a nice and a powerful result, and perhaps if I went through it quickly right now, it would be worthwhile to try and go through it more carefully on your own. The manipulations are very simple, but it's worth thinking where something would go wrong if the systems were not maximally entangled, and you will see things will go wrong if the systems are not maximally entangled at various points. Okay. The last thing I want to do is the page curve. But before that, if there are any quick questions, we can have them. Otherwise, if we can also have questions later. But if there are quick questions about this part before I go to the page curve, we can discuss them now. Okay. I always get a little worried when there are no questions, because it either means that everything was too simple, or it means that it was not clear. I hope it was okay. We'll come back to this in a few minutes.
Let me try to ask a question, if I may. So just precisely to see if I understand correctly.
Yeah.
Can we say that we proved that any typical state is maximally entangled?
Yes, it's one. Yes. So this is a manifestation of that fact. It's the fact that you take a typical state in the bigger system, and the smaller system is maximally entangled with the big system. And the manifestation we have of that is that you pick up any qubit in the smaller system, and its partner lives in the other side.
Perfect. Thank you.
Okay. So there is another way to say this, which is in terms of the entanglement entropy. And that is what gives rise to the page curve. In fact, we don't have to do any work to see this, and so it'll be very quick. So let's consider the entanglement entropy. Oops. So consider the entanglement entropy of the two systems. You see, if the density matrix is the identity, you can actually you could always take, by the way, so the entanglement entropy is defined as trace of rho log rho. And if the density matrix is close to the identity, you can expand it in close to the identity, and you'll get powers of rho squared and so on. And then if you wanted to compute the expectation value of this quantity with respect to the Haar measure, you could compute the expectation value of this quantity. This is not the expectation value in a state. This is the expectation value with respect to this Haar measure, which means you compute this quantity for a state, and then you average over states. And you would end up with the expectation value of rho square in the higher moments, as somebody said. But it's clear that if the density matrix is close to the identity, then we expect that this is approximately just S prime. And that's because if the eigenvalues of the density matrix are 1 over e to the S prime, you can check the trace of rho log rho gives you just S prime. Okay? But when we said it's S prime, remember I said that the eigenvalues of the larger density matrix were the same as the eigenvalues of the smaller density matrix. Right? So the entanglement entropy of the larger system is also S prime. Okay? And this, you see there's an asymmetry here. We are getting that the answer is S prime for both systems. And that asymmetry is just arising because we have made an assumption without loss of generality that one of the systems is smaller than the other system. Okay? So in general, the answer is that minus trace of rho log rho is expected to be the smaller of S prime and S provided the difference of the entropies is large. Okay, so provided S prime minus S is much larger than 1. Okay. So it could even be the case, this is just a notational trick. It could be the case that instead of S being much larger than S prime was much larger than S. That's why I put in the mod sign. But it's clear that the same argument would work whether one system was smaller, whether the system on the left was smaller, whether the system on the right was smaller. And so in general, the statement is that the entanglement entropy is a smaller of the two dimensions for a typical state of the big system. Okay, but if this is the case, then you can plot what the entanglement entropy is as a function of the fraction of system size. So let's say we plot, and this is the page curve. Okay, so let's plot S here, and let's plot X, which is S prime divided by S plus S prime. Okay, so this is this is telling you what is the fraction of the system that that lives in one system. Then you see that this just is going to go up linearly, because it will go up linearly till X equals half. This is X equals half, which is when S is equal to S prime. This maximal value here is just S prime is half of the dimension of the whole system, and then it will just come down linearly. The reason it starts coming down is because, so this is X equals 1, and this is X equals 0. The reason it starts coming down is because once the system becomes larger than half the system, you see that then the smaller subsystem is the system on the other side. So just to make this completely clear, remember we have a big system and we've made a partition somewhere in the system, and this is S prime and this is S. So I could have made the partition, and I'm moving this partition. So this is the partition that I'm moving, this partition in the middle. I can move it to the left or the right while keeping the size of the big system fixed. And if I move the partition to the left, then S prime becomes bigger. And at some point when I move the partition past the halfway point, then the entropy of the systems, the entanglement entropy, is controlled by the size of the smaller system. If I move the partition all the way, so the smaller system is very small, there's nothing for it to be entangled with, that small qubit can't have more than log 2 entanglement. And that's why near X equal to 0, the entanglement entropy goes to 0. But that's also true as X goes to 1. Once I make the system larger than half of the big system, then the entropy is controlled by the other subsystem, and therefore it again starts to drop. And once I'm at X equal to 1, which is here, the entanglement entropy again goes to 0. This point here is actually pretty sharp. This turnaround is very sharp in the thermodynamic limit. And that's because, what we are plotting here is X. And if X goes from 0.499 to 0.5001, you see that it's already this approximation that we were working in, which is that e to the s is much larger than e to the s. S mod of s minus s prime is much larger and 1 kicks in, provided the big system is very large. So if the big system has 10 to the 100 qubits, X is still ranging between 0 to 1. But the moment you go from X equals 0.499999 to X equals 0.500001, the approximation that we have kicks in. And therefore, this turnaround is actually really very sharp in the thermodynamic limit. And you see this characteristic curve. And this is the curve that is called the page curve. Okay? And it's a curve in that it's a curve as a fraction. It's a curve plotted as a, when you compare the size of one system to the size of the entire system. So far, this has just been kinematic. We will, in later lectures, in the next lecture, apply this curve to black hole evaporation and arrive at a paradox. And so we'll return to physics next week. But in this lecture, we've just discussed some preparatory quantum information results that will be useful, not just in the next lecture, but also as we go forward. So actually, I see we're already a couple of minutes beyond time. So let me stop here and see if there are further questions, and we can stop the formal lecture here.
Okay, there are a couple of questions in the chat.
There are a couple of
Maybe
questions in the chat. Yeah.
Yeah. Okay. So I think the first question is in this slide. Is S the entanglement entropy? And it's different from S of the larger
Indeed.
system.
Thank you very much. Yes, this is Sent. I should have been careful. Thank you. Thank you for pointing that out. So this S is indeed the entanglement entropy, which is different from S of the larger system. Thank you. Yes.
Okay.
Maybe I was careless about that. Here, I guess I was not. But in this curve, I was. Yeah.
Okay.
Yeah.
And there's actually one more question.
I can see in the chat. Yeah. Go on. Yeah.
Yeah. You can also see the chat. Yeah.
In the derivation, we require the operators to be pseudo spin such as a1 minus a2 squares, a1 plus a2 square is equal to 1. Yeah, it's not, I mean, it's a strong requirement in that we are choosing to focus on qubit-like degrees of freedom. So, you know, you see, what we're saying is that you give me a degree of freedom, you give me some big system. Now I want to find some violation of Bell's inequalities. So I want to say, I want to focus on one qubit in this big room. So, you know, this big room has many degrees of freedom, which I can divide up in many ways. It's most convenient for us to focus on a qubit. And when you focus on a qubit, it's natural to talk about sigma z and sigma x. But the real property we need is we want some operators that have this property that a1 square is a2 square is 1 and a1 plus a2 square and a1 minus a2 square is 2. As I said, it's a choice. It's just a choice of, you know, what operators I want to use to probe some degree of freedom. And if you have qubits, if you have spin systems, then these operators are just sigma z and sigma x. Sigma z and sigma x have this property. But in a quantum field as well, you could always locate such operators. And we will, in quantum field theory, find such operators. So the statement is, you know, you find me such pseudo-spin operators, and I'm allowed to use them in the Cytosins Bound. And then I will find for you a partner somewhere else. And the pseudo-spin is just kind of a way of making precise the statement that you find a qubit and look at sigma z and sigma x for the qubit. Now, I'm happy to answer more if there's more question about this. I don't know if that makes clear. It's more a choice. It's just, I'm just trying to make precise the sense in which we are focusing on a qubit.
Clear, that helps. Just a follow-up question. So does it mean that depending on the operators you choose to probe the system, you find a different entanglement entropy?
No.
The state, so say don't use this pseudo-spin.
Oh, sorry. I'm sorry. I was not clear about that. The entanglement entropy has nothing to do with these operators. The entanglement entropy, once we started discussing that, had nothing to do with these Bell pairs. That's just trace of rho log rho. So that is completely basis independent. It doesn't require any choice of basis. Before that, we made a separate statement, which was here, which was that, you know, if you choose some operators like a qubit, you can find its partner qubit in the other subsystem. But the entanglement entropy is a question of how many such partner qubits do you have? You know, the entanglement entropy kind of counts how many Bell pairs you have. And the number of Bell pairs is always like, you know, the size of the number of qubits in the smaller system. And that's just, so entanglement entropy is just counting. This other result is in some sense a more fine-grained result. It's saying, if you give me a qubit in a smaller system, how do you find its partner in the bigger system? And the entanglement entropy is counting, and that counting is basis independent.
Okay, yeah, clear. Thanks.
Okay, thank you.
Yeah, Rifat, I think Rifat has a raised hand. You can go on.
Yeah, go on,
yeah. The condition that the expression that you wrote down, the expectation value of the entanglement entropy is minimum of S prime. This is true only if S prime minus S mod is very greater than 1, right? Then in the page curve, we shouldn't be able to talk about the fact that when in the region when X is close to half, right? This result.
But notice that's what I said about the sharp turnaround. You see, X is close to half means how close to half? You see, let's say both the entropies are multiplied by some large number. So if you have some system which has, you know, a black hole. So a black hole has 10 to the 73 degrees of freedom or some huge number of degrees of freedom. So X is close to, you see, the more, if X is half minus 10 to the minus 10, or if X is half plus 10 to the minus 10, you are already in the regime where S prime minus S is much larger than 1, because you have to multiply this with the huge S that's sitting up front. Okay? So you're right that you can't talk about X exactly at half, but the size of this part where you're not able to talk about S basically goes to 0 in the thermodynamic limit. And there's a very narrow interval of X around half, which you can't talk about. But that size basically just goes to 0 in the limit when these system sizes become very large.
Okay, thank you.